So to illustrate the solution of the eigenvalue problem, considering higher degree of freedom, so let us try to solve uh, these models. Um, it's a 3DOF. It's a three-story shear building model, which is actually converted into an analytical model in the form of a mass spring system. There's no damper involved. So we are tasked to determine the response of the three masses considering the given parameters. But before we can do the response analysis, we have to first know and determine the natural frequency of vibration using several techniques that are very classical. So I want you to know this classical solution since in case there are no available software, you need to do it in a very simple iteration, so you can use a calculator if you don't have any computers. So for the free body diagram of this analytical model, so we take note that the resulting equation in the matrix format is simply represented by this differential equation of motion. And I'd like you to look into the pattern in which the degree of freedom uh, formulates the K matrix. So if you will observe in the two degree of freedom system, the K matrix has these components. So we have a K1 plus K2, but since there's no third mass involved, so this becomes a K2 only, no? So there's no K3 here, and your system, since the 2 degree of freedom, is only this part, okay? While if you expand it into a third degree of freedom, so you will notice that the simple modification is that you add up to a K2 plus K3 and then a K3 there will end the last element of the matrix. And of course your negative K2 and negative K3 is to take care of the symmetric pattern of your K matrix. No? So for a fourth degree of freedom system, you expect a very typical K1 plus K2, and then a K2 plus K3, and then a K3 plus K4, and a K4 system, no? Wherein your negative K2 here will complete no? The bandwidth of the matrix and make it diagonally symmetric. Okay, so negative K4 there. Of course, the pattern involved here is only good for regular modeling such as this one here. In cases wherein the stiffness are joined in complexity, or like a stiffness is K in series, in parallel, etc. So the pattern will not be straightforward, but you can think of it as you can think of this as a guide for you to be able to formulate it without the need of the FBD. Of course, the last resort in order to check it is to use the free body diagram. So to solve for the determinant of this eigenfunction, wherein your resulting matrix will now be in the form uh, k squared minus omega squared m, okay, must be equal to 0, is an assurance that this has a non-trivial solution. And doing the standard determinant process, it's very difficult not to do it at this stage. That's why some techniques which I'm going to give you now in the form of a flexibility equation will help you do uh, the computation. So for the flexibility method, we take into consideration that your equation which leads to your eigenvalue solution is in this form. Okay, so this is a simple ky is equal to omega squared or minus omega squared my is equal to 0. This came from the original equation of the DEM, which is m y plus or double dot plus ky equals 0, no? Wherein y was assumed, okay, to have a solution in the form of the exponential function e to the I omega t. Okay, so if you take the double derivative of this, you will end up into a negative omega squared e I omega t, and your y becomes negative omega squared y double prime is negative omega squared y. Okay, so if we substitute this in this original equation, this becomes m minus m omega squared y, which is this one, and your ky is this one here. So for your flexibility formulation, all we know about flexibility is that this is the inverse of stiffness. Okay, so if we take the inverse of the stiffness, which is in this form, k to the negative 1, we are actually applying what you call the flexibility method. So if we let k, this part here, to be equal to d, k to the negative 1m, and make an iterative solution in the form of a method of false position, okay, wherein y is actually equivalent to y, so you assume a value of y, then you check if the value of y will match the first iteration, then second iteration, third, fourth, until y here becomes equal to y on the other side. So doing that, we now start our iteration, but of course we have to first to deal with the k to the negative 1 m value, which is this one, and this is not very difficult if you are using a software or a MathCAD or a MATLAB or an Excel application, and begin the iteration by assuming your amplitude, your mode shapes to be 1, 1, 1. Then your first iteration, okay, will yield to this value here. Okay, so this is actually y is equal to y divided by 1. So this process here is what you call normalization. Okay, so you simply normalize it to unity so that it's easier to look into the result. Okay, so this y here is divided by the first. These y's here are divided by the first value of your y. So this is 003 divided by 003 is 1. 005 divided by 003 is this one, and so on. Okay, and if you are going to do the same with the second iteration, you will get this one, and so with the third iteration until it reaches the last iteration here. So sorry for the unreadable formula here. So I converted it in a PDF. That's why sometimes there are problems in the conversion. But what I'd like you to take a look into here is that the value of y, 5 and 6th iteration, are almost the same. So we can stop right here. Note that the natural frequency then was not included in the decomputation. So if you look at the decomputation here, your d is only k to the negative 1 of m. Okay, so the omega squared here was not included, so we have to do a little bit more computation here, so such that your omega squared dy now is equal to y. And what is your dy? Your dy is actually this last value here divided by your y is this value here divided by dy. Okay, so this is now your y, which is 1, and your dy, which is 0.005. And then your y here is 2.148 divided by this one. Dy is this one and this one. Okay, so with this amplitude, which are actually the eigenvectors, we can arrive with very near values of omega. And if we take the average of the three, since it's just an approximate method, we can come up with a conclusion that your omega might be in this level of magnitude, which is 14.395. And this is the first mode of vibration, or the fundamental mode of vibration, which actually is captured by the stiffness formulation. So unfortunately, with this stiffness formulation, you can only get one value of your frequency, natural frequency, and so we need to take a look on another method. Sorry, this is the flexibility formulation, and we need to look at another method, which is the stiffness formulation in this form. The procedure is almost the same. Okay, the only difference is that the stiffness formulation is now straightforward. There's no k to the negative 1. It's a k there, and your coefficient b is defined to be in terms of m to the negative 1k, and using that b to come up with an iteration here, 111. So everything is just the same. Okay, so you come up with these values: 100, 1 negative 0.530, and if you will observe, the iteration becomes very numerous at this point, because we want to make sure that the convergence, the last iteration, will actually yield to some level of accuracy in which your ninth and 10th equation will actually give you a very near values of your y there. Okay, so since the values in 9 and 10 are almost the same, we can stop here and note that the natural frequency as we have done on the flexibility formulations. We just do the same. 1 over omega squared is byy, and then we solve for omega squared. Simply this is your by. Okay, 2.122 divided by 1 is 46.065. And so on and so forth. We take the average and get your value of 46.06 as your last mode. Okay, so take note that the flexibility yields the first mode or the fundamental mode, while your stiffness method yields your last mode. In this case, it's the third mode of vibration. Okay, so that's it. In the next video, I will be discussing to you the whole source method, which is a little bit different in principle rather than these two formulation I have just discussed.